Okay, welcome everyone to my continuation of what are my favorite theorems. As usually, right? My favorite theorems. So my very, very own biased point of view. And actually, strictly speaking, I don't want to talk about a theorem today, but more like about philosophy and a few theorems associated to that philosophy. And what I would like to talk about is kind of the the art of locating roots. And by that, I will mean that we'll take a polynomial and you want to solve a polynomial equation because, well, that's what mathematicians do. That was what almost all mathematicians do, solve some kind of polynomial equation. But as we all know, I guess, solving polynomial equations is pretty hard. If you want to solve them explicitly and algebraically, you're basically dead from degree 5 onwards. So what can you do? And the philosophy is a little bit like, okay, maybe we can't solve them, but maybe we can kind of locate the roots in a different way, in a more efficient way, for example, in the sense that you don't need to solve the polynomial equation that you can't solve, but rather there is a very easy read-off criteria and you get a bound for your solutions. Okay, but let me just start very, very easily. So there is one of the most important theorems in algebra, and it's called the fundamental theorem of algebra. And the statement is basically that any polynomial has a root in the complex numbers. Very good. And complex numbers for me always means I plot them here in R2, as you can see. So here is a picture I stole from a Mathematica project linked in the description, which I won't run because I have, well, it's not super important for what I'm going to do, but it basically, well, as you can see, you have this polynomial here of degree 7, and you have those 7 roots. Here's 1, 3, 2, 3, 4, 5, 6, 7, and depending on the coefficient, this program will plot the roots in C, in R2. And if you would run that, and we'll run a different one in a second, you will see that the roots kind of uh, vary continuously with the parameters. So the parameters will be the coefficients, and if you kind of increase them a little bit, then the roots will vary a little bit, and so on, and so on, of course. And if you increase them a little bit or decrease them a little bit, then the roots will vary just a little bit. And this might tell you that there might be some hope instead of just calculating the roots explicitly by just bounding them. You start with a very easy polynomial where you know where the roots are, and then you vary that polynomial a little bit by varying the coefficients, and you might end up with a certain region of where the roots could lie, right? I will show you a lot of examples of such regions or such formulas where you can locate polynomial roots. And so that's kind of the question I would like to address. So how can we actually avoid those calculations? Because we just can't do them in general, right? Um, there are two ways of attacking that problem, or maybe even more, and at least two ways. The first one would be to find approximate solutions. And that's usually what Mathematica does, like let's say Mathematica. This plot here for this polynomial approximates the roots, and that works pretty well. But if you want to do some kind of pure mathematics and you want to have nice and clean statements, that's something you just can't do, right? You want algebraically exact solutions. And as I said, that's just impossible in general. So this is a degree 7 polynomial equation, as you can see, and there's just no hope you can write down the roots explicitly. So the second approach that comes to mind would be the one I'm going to discuss, namely write down a nice bounding set, like a circle, and then you can at least say, oh, all of my roots are in this circle. And then you might want to play around with that a bit more, because now you have some like, really precise statement, not like the root is approximately xyz, but really the root I'm looking for is in set xyz, and yeah, maybe you can do something with that. This is a really classical problem in mathematics, because people were looking at polynomial equations for quite a while. So the oldest theorem I found goes back to Gauss. So Gauss had an approximation theorem in this sense, which is linked in the description in my material list. If you want to have a look, I'm not discussing that theorem itself. I'm discussing two other theorems which have such a slick and nice and clean statement. I'm really impressed. I love them really much, and I love them a lot, as I said, and I hope you like them as well. Point will be they have an extremely clean statement, and they do a really good job, as I'm going to explain. Okay, summary, because I already started waffling. I want to draw the circle, basically. I want to have a good formula for the circle, depending on the polynomial. And the first theorem I would like to discuss is something you might have seen in complex analysis. Usually it's not discussed, at least in my experience in complex analysis, is a theorem by Rouché. Hoping I pronounced the name correctly, of course. And it works as follows. It's a pretty easy theorem, and it is much more general, but maybe the main application is for polynomials. So the idea is basically what I just explained. Polynomial roots vary continuously, so maybe it's enough to check them for some dominating polynomial, dominating part. So my f here will be this dominating one. And then I can say something about everything that is smaller than f. And I can bound the roots. And it works as follows. So I have my dominating polynomial here in my example. It's z to the fifth. And yes, I can calculate the roots of z to the fifth. They are, well, all zero. So counting with multiplicities, there are 5 roots and they're all 0. Okay, and you have this funny statement that if my function dominates this function, which is a funny one, it's basically I want to cancel f's here and then g remains, but the function I'm interested in will be f plus g. So I just leave it as it is. So if I have this inequality at a certain bounded region, and it doesn't really matter what this region is, so let's say a circle, then actually I know that the number of all roots lie in this circle. So here's my circle of radius 2, and of course these are the roots. So I should have 5 of them because I'm looking at the degree 5 equation here, which I will run Mathematica in a second here. Okay, an explicit example would be I could take f to be, oh, that was bad. I could take f to be z to the fifth, and I could take g to be this one. So the polynomial I'm really interested in is f plus g. And I kind of chopped off its dominating hat. I know what the dominating hat is doing. I just checked that g itself, look at this equation, right, at cancel f. G itself is smaller than f on a certain radius, which is very easy to see. And the theorem then tells me that all the roots are located in a circle of radius 2. So let's actually have a look at Mathematica. So here's Mathematica, and it's the same setup. I have my polynomial z fifth, z to the 5, plus a times z plus b, and I can vary a and b here. And as you can see, if I vary a or b, it doesn't matter. This is funny. Okay, this is funny. The roots change continuously with the parameters. But the point is, no matter what I do here, so b and a run from -10 to 10. We go back to my slide in a second, and I have my circle of radius 2. And no matter what I do, if I run from -10 to 10, they get pretty close to the boundary. You can't see this at the bottom, but it, of course, just behaves the same. It's a mirror of this on the top. So just have a look at it on the top. Anyway, it gets pretty close to the boundary. As you can see, it actually hits the boundary almost. But it never goes across, and that's exactly the statement. So no matter what you do, well, it never goes outside of this circle, which is kind of a funny thing, right? So it is, for this polynomial, for example, when a is almost -10, it's and b is whatever this is, b is -6.8. This is a pretty good bound. If both are around 0, it's maybe not the best bound. So you might want to play around with it a little bit more. Okay, let me come back to what I just did. So a ran from -10 to 10. So -10 to 10. And b was the same, also from -10 to 10. And if you just look at this equation, so So this would be whatever, let's say 10 times z plus 10. And all you need to do in this case is a very easy one. I claim if I take z equals to 2, this is smaller than 32, because that's kind of what I need to verify. And let's see, oh yeah, it's 30. Yeah, so yeah, this is 30. So it's smaller than 32, though, so the theorem applies. And the closer this number goes to 32, the closer the roots are kind of at the boundary in the extreme case. But well, let me summarize. This is actually a pretty nice theorem. It's pretty easy. You chop off the hat of the polynomial, the leading term. I show you another explicit formula like Rouché or a certain one later, but you basically chop off the hat and you can determine the roots by just looking at the basically how fast the hat grows. Just kind of a very nice statement. And the proof is not hard. The proof I think is on Wikipedia, which is linked in the description. A little bit more elaborate, at least from the proof, not much more complicated, but also very nice and very easy to remember, is the so-called, and I show you, I think, 3 variants of the Eneström-Kakeya theorem, and it works as follows. So you again have a polynomial, but now your coefficients are real numbers and they're ordered. You have this nice ordering. Then you can do much better, right? So here I had this problem that the bound depended on my leading coefficient. And here I don't have this problem anymore because the circle I need to draw is always of radius 1. Okay, so for example, here my polynomial 10, 9, 8, 8, 2, 1, which I have absolutely no chance to solve algebraically. It's certainly ordered. That's very easy to check. So all of its roots that you can see up here are located in this circle of radius 1. So let's also have a look at that theorem in Mathematica. So here we are. It's exactly the same setup. I have my polynomial a, b, with coefficients a, b, c, d, e, and f. And I can vary them up here. And this is exactly the picture you've seen before. So the 10, 9, 8, 8 to 1 picture. And again, it's the same thing. I can vary here my f. And as long as these are ordered, my roots will stay in this funny circle. As long as these are ordered, everything is fine. And as you can see, maybe I need a little bit more, so I can pull this one. I can pull this one up, and they vary quite a lot, and they still stay in this circle. As soon as I do something different, you can already see they move outside. So this is a very, very, well, the bound is actually pretty good. So here they move outside, but sometimes it's not optimal. So as you can see, this is not ordered anymore, but the roots are still in the unit circle. So it's certainly not optimal, but it's pretty good. Okay, so here's another one. As long as they are ordered, they stay in the unit circle. That's a pretty easy to remember statement, right? You just have ordered coefficients from the leading one, should be the biggest one, so for the highest power down to the coefficient of the identity element, and it's pretty easy. They always lie in the unit circle. Pretty nice statement. Proof is not very hard. Link is in the description. Right. So kind of the philosophy, if it wasn't already clear, is don't calculate roots, locate them. And you have several theorems like that. Link is in the description. It's a nice paper, not very hard to read, something like 10 to 16 pages, and it lists a lot of those theorems. I'm just very biased. I took the one I like the most because they're the easiest to remember. So I showed you this dominating theorem a la Rouché. I showed you the order theorem of Eneström-Kakeya, which also exists in the reverse order. Then the statement is also reversed. So this just means all roots lie outside of my unit circle. So they are somewhere here. Right. So if you have the reverse order, everything lies outside, which is also very nice and easy to remember. There's a strengthened version of this theorem, which I'm going to show you on the next slide in action, and then it is Mathematica in action, which doesn't have any ordering anymore, and you can still say something. You then will say that things lie in a certain annulus given by the coefficients. So an annulus is this thing. So you have this nice color, and your roots are somewhere here. Also a very nice statement. And then there are variations of this. So we can, for example, drop the the condition of being non-negative, then you have something with order, and you can still nail it down pretty good, pretty nicely, and pretty smoothly. So there's a whole industry of deriving those formulas, and sometimes they're just very useful for what you do, and you just need to find the right one. And that's why I like the summary paper in the description, because it lists quite a few variations which are non-trivial. So if you want, you can have a look. But to wrap the whole thing into a nice package, let me just show you that you really want to look at different formulas. So one of them is not enough. So let me compare for different polynomials the one I showed you, the Rouché, and kind of the best you can do is to use this bound, or not the best you can do, but something you can do from Rouché is to use this bound. So the absolute value of z is smaller than the maximal of the coefficients, plus 1. And this gives me the green circle. So that's the radius of the green circle. This was a horrible circle. Anyway, so here's the green circle again. And you can see here I have two different polynomials, and I haven't varied them much here. So the only difference is this is 1.85 and this is 0.22. But the picture is very different. So here you have the promised annulus, which is the blue one. So that as you have an outside annulus just means you have an outside circle and an inside circle, and your roots, as you can see, here you are. They all lie in this annulus, and for this polynomial, the annulus is a much better approximation than the green circle right outside. For this picture, the annulus is just tremendous. It's outside here, and it has a very, very almost not visible circle in the middle. So the green one is much better. So let's have a look at Mathematica actually. So here we are, Mathematica, same setup. My polynomial is up here. The blue circle is Eneström-Kakeya, and the green circle is Rouché. And I can vary my coefficients here. And as you can see, very much depends on the polynomial. The point is the outside circle, remember, was just the maximum of the coefficients plus 1. So as long as I don't touch this, oh yeah, okay. Let me turn this a little bit lower. As long as I don't touch this 3 here, or I go over this 3, the green circle actually doesn't vary. The picture, however, is fixed. So the green circle actually does vary. You just can't see it as long as the blue circle is smaller, because the maximal frame of this picture is just the green circle itself in this case. So even if I increase this one, only the blue circle will change. So don't be confused by that. But as soon as the blue circle gets really smaller than the green circle, picture turns around. Like if I draw like this, as you can see. Ooh, it was too quick. Okay, so now depending on your polynomial, so this one, for example, the blue circle or the blue annulus looks pretty good. In my opinion, it's a good approximation. The green one, not too good. But if I just vary this up to a certain point where it just turns around, where the blue circle gets bigger than the green circle, the green approximation is just much, 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 much better than the blue one. Yeah, so in practice, if you really want to use those theorems, it makes sense to look up kind of a list of theorems and then just check whatever is best for the situation at hand. Yeah, but let me wrap up, or let me summarize. So what I tried to tell you today is this idea of, instead of computing polynomials explicitly, try to locate them in some nice geometric regions like circles or annuli. And there are a lot of theorems out there that do the job for you. Again, I said again, the link is in the description to a very nice summary paper. And maybe if you have a certain problem giving a certain polynomial that you can't solve, maybe one of them helps. But I think the idea is also pretty nice and pretty striking. So just instead of solving something explicitly, solve it kind of in a form of cloud thing, right? It's somewhere in a certain region. Yeah, but I hope you enjoyed the video, and I also hope to see you next time.